Yeah, thanks for sticking around so late. This is the Beyond the Basics session for the JavaScript API in 3D. So my name is Joe. Here is Stefan. We're both from the Zurich R&D office where we develop the 3D part of the JavaScript API. And yeah, since this is the kind of the more advanced session, we assume that you've already used the 4X API a little bit, or at least like seen 4X API code a bit, and maybe already turned a map view into a scene view or used a scene view. We're not going to cover the very basics here, but yeah, hopefully that'll be good for you. Yeah, we have a lot of code, a lot of different samples. Hope it's not too much, but let's see. Let's get going. Here's the agenda. I'm going to first talk a little bit about the architecture of the API. If you've been in the getting started section, this is going to be a bit more technical, a bit with a bit more detail. Some more things that we're then going to use later. And then I'm going to talk about using the scene view. And then I'll hand it over to Stefan, who will talk about more advanced techniques for interacting with data, including filtering and like a sample combining filtering and other things with symbology. And then finally, he's going to talk about a very important topic, which is striking a balance between performance and quality in your app. If you've used the scene view already or the scene viewer, you might have noticed that once you start adding a lot of data, things start to get slow, and other things happen. So Stefan will talk about that. Cool. So let's dive into the architecture. Here's like just kind of as a recap, a very basic short app. So this is kind of like the most basic app you might want to make. You create a map, which is the description of all of your data. And then you create the view and pass a map into that view. And then you're creating your layers and adding your layers to the map to have data in that map and view. And conceptually, what this looks like is this here. We have on the left-hand side the description of the contents of your scene, which is what you add into the maps. And this is mainly, like, for the most part, this is layers that you add to your map that describe what you're mapping, right? And then on the other hand, on the right-hand side, we have the scene view, which provides a view onto that map. And the view renders the map, and it handles user interaction with the map. So yeah, if you're familiar with the model view pattern in other programming languages or other frameworks, this is kind of a little bit like a model view situation here. What's also there is the layer views, and this is something we haven't talked about too much, and we're going to talk a little bit more about it later. So the layer views, internally, the API creates a layer view for every layer that you add to the map. So just like we have the scene view being kind of the view onto the map, the layer views will be the view onto the layer. You don't have to do that yourself, obviously. Like if you've done this before, just adding the layer to the map will already draw that layer. This is done automatically internally, but for some of the advanced functionality that we're going to talk about in this session, you will need access to the layer view, and so this here completes that picture. And then, like a broader overview of what's 3D and what's 2D is this diagram here. We have seen the left-hand side of that in the previous diagram. So the scene view that's connecting to the map. You probably already know that if you want to create a 2D map, you instead use a map view and connect that one to the map. So you can use the map with either a scene view or a map view. But if you want to also be able to store your map, to save your map to ArcGIS Online or Portal, then you can actually, this is not built into the map itself. And also, this is not unified between 2D and 3D. Depending on whether you want to save a 3D scene or a 2D map, you have to use either a web scene or a web map to do so. Because these are, in our data model in ArcGIS Online, these are two different types of documents. The web scene and the web map objects, they both inherit all the functionality from a map. So anything you can do with a map, you can also do with a web scene or a web map. But on top of that, you can also load them and save them. At least web scenes, web maps cannot be saved yet, but this will come in one of the upcoming releases. So I want to also talk about a few concepts that we use in our API that are kind of important because they are used throughout the API, and it's important to understand them so you know how to work with them. The first one is properties. So we've tried to really, in the 4X design, we tried to really unify how you access our classes or our live objects, and not only access but also configure and do things with them. And so we've introduced the thing called properties. You may know this from, this is not new, from other programming languages. One of the perks of it is that you can just read or write these properties directly. And let's look at a sample of that. So here's the scene viewer. In case you didn't know, you can actually access the scene view of the scene viewer if you just open the console and then type view, and that can actually be useful to try things out. So here I just want to change the base map, let's say. And instead of having to call like a set base map function or something like that, I can just do set base map equals, and then I can pick maybe satellite here. And that will immediately change the base map. So behind the scenes, we realize that you've assigned a new value to that property, and we do whatever is needed to reflect the new state of it. You can also then just read out what the current base map is. However, that may look a little weird to you here. Is the code large enough? Make it a little larger, maybe? All right, here we go. So now I've set a value here, the string satellite, and when I read it back, I actually get an object back, and there's some stuff in it, like typo, it says imagery. So what's going on here? This is part of the automatic type conversion that we have, which we call autocasting. If we go into the documentation for the base map property, so this is the web scene. This is the API reference for the web scene. You can look at all the properties that we have here. Base map is one of them. And base map actually has the type base map. The property called base map has the type base map, capital B. So this is a class that's also defined here. You can see it has like a set of base layers and reference layers. This is how we store the base map in the API. But we want to often have these convenience setters kind of that allow you to assign, for example, a simple string like topo or streets or satellite instead. And what we do is on writing this property, we convert it to the internal representation. So when you look at the documentation, this base map here is what the property, the type of the property it really has. But then you can read here, this autocasts from string or object. And what that actually means is then documented down here somewhere. So this is used in many other places. For example, if you set the center on the view, you can either give in a point, you can set it with you can assign a point to it, which is what it really has internally. But you can also just do an array with latitude and longitude coordinates. So this is all described in the doc here. Right, so that's autocasting. Another nice perk of these properties is all the properties, you can initialize them in the constructor of the class. So if you look at this code here, any public object as a first argument to the constructor takes an object, and with that, within that object, you can just list any of the properties you would like to initialize and put the values in there. So we don't document the constructor as what you can put in there. It's really just all of the properties of the class. And finally, you can watch for changes on these objects. This is what we do internally when you assign something to it as well. Watching for changes, we can look at this in practice again. It's very simple. So watch means you will get notified when the property changes. So you can just do view.watch and then list the property that you would like to watch for, and then a callback function that will be called whenever that property is changed. And here we can just do something simple. something like that. So it just logs a string to the console. And now if I change the base map again, let's change it to back to topo. Oh, that didn't work. Oh, of course, sorry, I did a mistake here. The base map is not on the view object, but it's view.map.watch base map. All right, and then let's switch to base map again. Oops. Here we go. Now you can see that, yeah, I installed the watch twice. I'm not sure why that right here happened, but you can see that this function was executed, the printed base map changed. Obviously, you can like read the new value and somehow react to it. So these are all really nice utilities that we use internally heavily, but you can also use them when you write your apps. And that's how all of our public classes are structured. All right, then another concept that we use heavily are promises. Who is familiar with promises in here? Please raise your hand. All right. Who has never heard about it? About what a promise is? Okay, let's do this very quickly. When you write a web application, you often have asynchronous processes. Like, for example, you need to fetch a document, and while that is fetching, you don't want your application to stop, you do other things. So you want to get kind of a callback whenever the document finally arrives, right? And so this used to be done with callbacks previously, so you would call, So you would do something like fetch data, and you gave it some URL, and then you had like a callback function. Well, let's do this anew. So you get the data back, and then you kind of handle your data here. Something like that, right? And this has a number of shortcomings that were identified long ago, and promises have been established essentially in the JavaScript world for quite a while now as a new way for handling this. There's another new one, async await, which works well with promises. What it allows you to do is instead of having to pass in a callback function, your function that is asynchronous will return an object. And that object is a promise to deliver the data that you want at a later point in time. And you can install a handler on that object to be notified whenever the data changes. So geometry service project is one of them. That's one of the API functions that projects a geometry. And that goes back to the service, does the projection there, and then comes back with the result. So when you call a project, the return value will be this promise. And then on the promise, you can call a function .then, and then put your error handler in here. And you can also, that way, with that catch, install you can install the result handler in here. So here, for example, there's a result, I get the converted geometry back, and I add it to my view. Or maybe if there's an error, then I display an error message. You can also chain promise. Let's skip over that since many of you have already heard about it. One reason I'm talking about this is because in the API we have a few other kind of similar, okay, so that's still on that slide. In the API we have a few classes that kind of behave like a promise. Specifically scene view, map view, and layer all have some kind of asynchronous initialization component to it. So for the scene view, it will only be able to display something once you've assigned it a div, like a view container, and a map, and there is some data in that map. And only then the view will become active and available. And the layer, for example, a feature layer, first needs to fetch the service description from the service before you can actually work with it. So what we did is we made these classes kind of promise alike. We gave them a function .when. Maybe you still remember this being .then. At the beginning, when we released, it was layer.then, view.then. We had to change that because it caused problems with promises, with native JavaScript promises. So in one of the past releases, I don't know, probably about 3 releases ago, we changed that from then to when. But other than that, it still behaves kind of the same as a promise. So you can do view.then, and in the handler, you can then return a new promise, and then you can start a promise change like that. Layer views, we've already talked about them. They are being created by the API automatically whenever you add a layer, but they're also created asynchronously. We load in additional resources before we can actually create them. So when you add a map to the layer, the API will start creating the layer view, but it will not be immediately available once the layer is added, once that function, that add call returns. So the best way when you need to work with a layer view to retrieve it is the function when layer view on view. You simply call it and you pass in the layer of which you're interested in the layer view, and this function will return a promise, and that promise will then resolve to that layer view. So that is kind of the best way for you to get to a layer view for a given layer. There is also a collection of layer views on the view. So that's kind of like an array, but we have this internal collection class. This one contains all the currently created layer views. You can use that in certain situations when you already know that the layer view has been created for sure. Then it may be easier to work with that. But just beware that, when you're not exactly sure that that layer view is already there, you shouldn't use all layer views, or you might not find your layer view in there. Also, in there you just have to go through all the layer views and figure out which one is the one that belongs to my layer. All right, so that's the theory part. Now let's move on to, the foundation part. Let's move on to some more detailed description of what you can do with the scene view. You probably already know a little bit about that. So I'm gonna go over some of the basics that you may already know, but then point at some maybe less known capabilities of the scene view. The first one, most important one, a very important one is the camera. So view.camera stores the current viewpoint of the scene. It stores how the view or how the window is currently looking into your map. And this is really the kind of the ground truth of what the camera is. We will see that there are various ways to change that view, but this is what reflects the current state, and you can also set it directly if you want. So the camera is made up of a position, which, like if you think of the camera as being your head with eyes looking somewhere into the scene, then the position is the position of your camera within that scene, the position of your head within that scene. So that defines the position, and then we define the orientation of the camera with the two angles heading and tilt. So heading is the deviation from north. A heading of 0 means you look north. A heading of 90 means you look east in a ENU coordinate system. And then the tilt is whether you look up or down or straight. So a value of 0 degrees is you look straight down at the map. It's kind of like the 2D view of the map. And then a value of 90 degrees is, means that you look horizontal, and a value of 180 degrees means you're looking straight up. So as I said, that's the ground truth, but this can be kind of hard to work with. Another aspect of it is, here's a demo of how you could work with the camera. If you want to change the camera, you always have to, you can't modify it directly. You can't do view.camera.position.x equals something. It will not automatically update. You have to set a new camera object to view.camera for it to work. So kind of the canonical way to do it is you first create a clone of the current camera. And then in this case, I'm increasing the heading by 5 degrees and then set the new object on the view. So if I run this, you can see that whenever I click it, I make a step of heading of 5 degrees in heading to the right here. You can also see that this happens immediately. When you set the camera jumps to that new location. So there's a few problems with that. First of all, if you now need to figure out, let's say you want to look at a building somewhere and you need to figure out what is the position and the heading and the tilt angle to look at that building. That's actually a pretty hard problem. And the other thing is you may want to animate there. So for all of that, we have the view.goto function. This exists both on scene view and the map view. And it allows you to, first of all, specify very easily what you want to look at, and secondly, it will also create an animation to go there, and it allows you to customize the animation. So the first parameter to go to is the target, and scene view is really kind of like a Swiss Army knife of setting up your view. And so as a target, you can pass in many different things. You can pass in a camera This is the best way if you have a camera object and you want to animate there. But you can pass in a geometry or an array of geometries, and you can also pass in a graphic or an array of graphics. So for example, if you want to go to a layer, you can do go to layer.extend, and then it will go there. We'll see some of these examples in a bit. You can, in addition to the what you're looking at, you can also specify at which scale you want to look at, or from which position you want to look at that, or which heading or which tilt you want to look at that. So you can kind of parameterize the view in addition to the target. This is also part of the target object. And finally, in the options, you can configure the animation. We have a sample for that. One last note is that the goTo returns a promise, which will resolve whenever the animation is finished. So if you want to create kind of an interactive experience where you go here, then there, or start blending something in once you're there, you can do goto.then, and then do whatever you want once the animation has reached the target. All right, so let's look at a few examples. Here's again a very basic one. Remember, like in the one before, we've already just increased the heading. So this one takes the current heading of the camera, increases it by 30 degrees, that's our new desired heading. And then it simply does view.goto, and the first parameter, remember, is this target object. And in the target object, you can simply provide a heading as well, or one of these other parameters that we've seen here. Scale, position, heading, tilt. What that means if you do that is that the goTo will preserve the current thing that you're looking at, which is kind of the view center. And it will just try to obtain the viewing situation that you prescribe here. So if I run that, you will see that it spins around the center of the view, and it increases the heading by 30 degrees in every click. As I said, you can, as I've already said, you can use goTo to frame a graphic or a set of graphics. So let's say that, we add a bunch of graphics to a view, and then we want to make sure that the user can actually see those graphics. So here's a function, let's say that creates your graphics. Now you just call goTo, and as the target, you give it that array of graphics. And then in addition, we specify the scale and the heading and the tilt at which we want to see those graphics. And if we run that, you can see that these red cones were actually the set of graphics, and you could see that there was a nice and smooth animation, and now you have all of these in view. There are a number of options you can do. This is actually not all of them. Here's just a few. You can control the animation. The simplest way you can do it is you can say that I want to have a faster or a slower transition, and you can specify that as a factor. The reason why it's a factor, or why you may want to use a factor, is because internally we try to be smart, and we check how far the target is away. And if we see that this is actually a very small distance, we'll make a kind of a short transition, a very quick one. Whereas if we see, oh, it's on the other side of the globe, you'll see the camera starts zooming out and going to the other side, and it'll actually take several seconds. So if you don't specify any animation parameters, the animation may be very quick or very long, depending on how far the camera needs to go. And if you just want to say, I want it to be a bit slower or a bit faster, you can specify that speed factor. A speed factor of 2 means it'll go twice as fast. So maybe let's just go back, and because I talked a bit. So this was the original speed here. But if I specified the speed factor of 2, you'll see that it's much faster, twice as fast, in fact. You can also, if you want, specify exactly the duration of it. So if you specify a duration of 5,000 milliseconds, it will take exactly 5 seconds to get to the target. And if you want, you can also customize the easing. So easing is, if you look at this transition here, you can see that it starts slow, and then it's kind of fast in the middle, and then it becomes slow again. That makes for natural transitions, but you can customize that. Linear means it just like starts immediately and then stops immediately, so it creates kind of a more abrupt type of animation. And there are different options for that, which you can look up in the API reference. All right. Constraints, there are a few ways in which you can constrain the camera. In fact, by default, let's go to the scene viewer here. If you're zooming out, it stops at a certain point and you can't go any further. That also happens here. We do this because we don't want you to like get lost in space, essentially. Typically, you don't want to get far away. But here's a really nice sample that Richie Carmichael did from the APL team that shows you all the satellite of the world. And in this case, you can see that you can't actually see all the satellites because the standard view doesn't allow you to move thus far away. So on view.constraints.altitude, you can specify the range of altitudes which the camera can do or can assume. And if I run this now, and now try to zoom out again, you can see that I can actually zoom out and see all of the satellites here. But now I hope you can see this on the big screen. Now there's a second problem. If you look at the back here, you can see kind of this arc of satellites going around the world. And, but it kind of stops between here and here. This is because there's a kind of, for technical reasons, for WebGL rendering reasons, we can only render from a certain depth, we call that the near plane, to another depth that we call the far plane. Anything that's outside of these two planes, we cannot render. And so we always have to set these planes smartly to contain all of your content. And we try to give our best to do that. We have some heuristics that do that, so typically you shouldn't see it. But in this case here, it fails, and it cuts the satellites at the far back. And by setting view.constraints.clip distance, you can actually manually override the near and far plane. So in this case, we set the far plane to 200,000 kilometers. And if I do that, you can see that now we can actually see all of the satellites. All right, view padding is a useful technique if you have a user interface around your globe, like here, but you want this to be semi-transparent. You know, maybe these are just individual elements like here and here. So if you do that, you can see here that now, for one problem is that it may overlap, like the globe or your data may overlap with the UI. And also the globe is centered into the entire window, but because you're placing UI elements here, the kind of region of interest for the map is really only this black part here. And if you can account for that by setting view.padding in any of the sides. If you do that, then we will still render. If you see, if we zoom in, we will still render in the entire rectangle, but we will put the focus of interest into that area that you defined and drape it nicely around your UI elements. Another nice trick that you can do is you can change the background color. This can be useful. We'll see that in the next slide. There's a couple of steps involved here. So, I mean, first of all, notice that now we see only the globe, but no more background. The first step you need to do if you want this kind of visualization is you have to tell the view that you want the background to be semi-transparent, because this makes rendering a little bit slower, so we don't have that enabled by default. By default, it would always be just black if there's nothing rendered. So, but setting this means that you can now composite your view against your HTML background and any elements that you have in there. And then in environment.background, you can set a color. And in this case, null, 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 it's only important that here the transparency is set to 0. So it's, sorry, the alpha value is set to 0, so it's fully transparent. And we also disable the rendering of the stars and of the atmosphere. And then remove all the UI elements. And that means all you get with this kind of view is the actual globe or world. So here's a really nice sample of what you can do with that Raluca made. So if you want this kind of super thematic stylized maps, you probably don't want realistic stars and realistic atmospheres, but you want to kind of have this, colored scene like this. Another thing you can do with it is this overview map here. So here we have the big map is actually a map view. It's a 2D map. Could also be a 3D map. And then we have this little inset globe here, which is rendered by a scene view. So when I zoom in or when I move around, you can see how this updates. I think we're running a little low on time, so I'm not going into the code of that, but if you're interested in it, you can look up the slides, and then if you peek into the sources here, you can see how this is done. Well, since we're already here, it uses the same trick that we used before to make it transparent here. One of the views, the scene view. And then actually the linking of the two views is very, very simple. On the main view, which is the 2D view, we simply watch for the extent property to change. And then whenever it changes, we set the center of the overview view, which is this globe here, to the center of that extent. And that's all you need to do. That will immediately make it move around. And then I have some more code here to create that rectangle on the globe. Cool, so that concludes the scene view part, and now on to Stefan for data.
Right, so just as a quick disclaimer, quite a bit of the stuff I'm going to show you in this section will be part of the next release of the API, so that's not yet released, but it will be released in a few weeks. And I structured it around a very simple hypothetical example where we want to erase a part of a city because it's, let's say, old industrial buildings and actually repurpose that as part of this park, which is already here. So what I've done here is I just pulled in the location of trees in that city, of street trees. They have these little dots. And the first thing we need to do is somehow mark the area which is going to be part of this new part of this park. And one way to do that, and I'm using this example to introduce quite a few different concepts. One way to do that is the function view2map. And view2map takes a point or even just a mouse event and translates that into a map coordinate. So as I start clicking around here, I will eventually create a graphic which is then correctly drawn onto the map because we use this, we take the event, tell it not to propagate further so nothing else happens like pop-ups or stuff like that, and then translate that into map coordinates and use this point to create a polygon and add that to the view. Another way to do similar things is like, let's say I don't want to just randomly click on the map, but I only want to be able to select the trees and only use the trees as a point for my polygon, is the function view.hitTest, which again takes a point and translates that into hits. And then the results I'm getting, I check that the result is actually a graphic, so my frontmost object I hit is a graphic, and if not, I'm ignoring it. So if I do the same as before, I click just randomly on the map, nothing happens. But now if I click carefully on a couple of points, I will start, oh, I think I missed one here. What? Okay, that worked before. I think it's just the resolution here. There we go, we start seeing the polygon. So I really have to hit the points. It's not so easy. Here we go. Another cool thing in the new version is that this hit test actually delivers multiple results. So by default, they are ordered front to back. And what I'm doing here is I'm clicking on that building, and then I'm rendering each hit I have as a green point, and also rendering a line from the first to the last point. So here I'm creating a point graphic for each of the hits, and then I'm adding a line from the first point to the last point. And that gives me this nice result where I see that as I clicked on it, the first hit was obviously the building we saw, but there are quite a few other hits hidden behind here. And that's a new feature in the upcoming release. So to summarize these two things, view2map only gives you one hit. It gives you the first hit of what you clicked on. And by default, it only intersects ground. So it ignores all the scene layers or other layers you have in your scene. And hit test delivers you all the hits you have, but it only intersects the layers. It ignores the ground by default. And if you want to change this default behavior, you can use options on these functions to include or exclude different layers. This was kind of a manual process, but again, in the new release, we have a higher level utility to do that, and that's the sketch view model. If you want to create a sketch view model, you simply instantiate it, you give it a graphics layer where it will insert the things you're creating. And you also give it the view you're acting upon. And then I'm also adding this graphics layer to the map so we actually see then the final result. So now if I start clicking around here, I can draw this polygon. When I'm done, I double click, and then the polygon gets added to this graphics layer and gets rendered as a graphics and no longer by the sketch view model. Slice widget.
All right, cool. Yeah, just like a brief intermezzo. We didn't know where exactly to fit it. It fit best here. Sketch view model is kind of like way for users to interact with your data. And one new feature that we released in the December release is the slice widget. And so I would like to briefly show that to you. So here we have a building scene layer. And maybe you've seen me do this in plenary, but you may want to slice into that building scene layer to see what's inside. And this is really easy. So the code here, first it adds the building scene layer. Then all you need to do is create the slice widget. It's called slice. You give it the view and it will install this little widget here that you see on top. Oh, it'll install it if you add it to the UI. But that's all you need to do. Now the user can click on new slice here and, for example, create the slice plane here and then move it around. And this all happens automatically. You don't have to do anything about that. The slice plane can be rotated. Layers can be excluded from the slice. So if I click on these pillars here, for example, let's make this a little more interesting. You could see like only the structural parts of the building. Yeah, you can create a new slice. We try to be smart with the alignment. First of all, we figured that all you ever want to do and ever need to do is either horizontal or vertical slice planes. If that's not the case, please let us know. If you need kind of slanted slice planes in space, let us know. For now, you can only do horizontal and vertical, and we analyze where the mouse is hovering, and based on that, kind of initialize the angle. So if I go on the roof, we'll create a horizontal plane on the roof. If I go somewhere on the side, it'll be aligned to that side initially. But if it's vertical, you can still rotate it around in that axis. You can just not tilt it. Yeah, and the last thing, maybe let's change this bit here, that I've also shown in the plenary is that like one of the useful things that you can do is once you've sliced it, oops, you can actually measure inside. So let's instantiate a direct line measurement widget and add that to the view as well. So a new widget pops up here, and now I can activate the measurement widget. Oh, this is a bit unfortunate. Activate the measurement widget here so that the user can measure inside that building. Very easy stuff. There are many more widgets that you can use. These two are kind of the 3D specific ones, which is why I wanted to highlight them here. But there's lots of very easy to use widgets, for example, to search and jump somewhere, and many other things. So you can just check them out in the API reference.
Cool. Now let's get back to our little redevelopment project. I've shown you a couple of ways how you could actually draw these masks. Now let's use them to filter stuff. In general, as an introduction, we have filtering on the layer and on the layer view. And what that conceptually means is that filters on the layer are applied when we fetch data. So if possible, we do that server side. There are some services which don't support that, and then we will filter the data client side. But the data will never be added to the layer view. It's really filtered out hard. And filters you do on the layer view, they are done client side, but they don't actually remove the data. They just make it invisible, so you can very quickly update it as you maybe move around stuff or change your filter. Let's do some one server-side filtering. Here, I just set a definition expression on the filter to say I only want to see the trees which are in good health. We'll use that later for our little park, because once we redevelop it, we will get rid of all the trees which are in a bad shape. Client-side filtering, for example, here I'm using one of these masks I've pre-drawn, and no, I'm using the schedule model again to draw the mask. So I'm starting to create my mask. And as you can see here, only once I'm done with it, we will grab this polygon which we created and use that as a feature filter and only show the data which is inside the polygon. So let's finish this one. And then all the data which is outside of that region is filtered out, and that's done client side. So when you move this mask around, it updates quickly because we don't have to go back to the server. Now let's use these filtering capabilities to apply some symbology to get to the result how this new park extension would look like. So first what I do is I create two feature layers, one which we will use to style the outside and one which we will use to style the inside. And we use different spatial relationship to filter everything which is inside or everything which is outside. As you note in my inside filter, I don't show that in this pseudo code here, but my inside filter only still shows the healthy trees, whereas the outside layer has all trees. Let's style the outside, because as we did see here, there are a lot of trees and they kind of overlap and there's still points, so a person won't know that they are trees. So since they're outside, we are not that interested in them. We just use a point symbol with a little 2D icon, which is a small tree, which takes a minute to load and render. And then also we apply feature reduction in it, so we don't have any overlapping trees. And additionally, improve the perspective appearance of these trees. So the trees in the back are a little smaller. They're not actually with 12 pixels, but the trees in front are 12 pixel sized. There are no overlapping trees, and that looks nice and tidy. Now let's style the inside a bit nicer. For the inside, we are using web style symbols. So these are models which are provided by Esri. And these models also have different levels of details, which means that if they're far away, we use a very simple model, and if they are really close, we use a complex model, and that allows us to visualize way more trees than if we would just use the complex model for all of the trees. So you already see some of the complex trees have loaded, and we got the whole outside styling we did previously. And now if you go closer as well, you see that they are really nice tree models, and our new area of the park would look like that. With that, I'm done with this part of the talk, and we'll move over to a few hints and tricks on performance and quality trade-offs. The simplest one and straightforward one is to use the quality profile and quality on the scene view. And these settings affect the level of detail of a few set of layers, so all the map layers, the ground layers, and also of the scene layers, like 3D object scene layers, and also integrated mesh layers. And they enable a few other rendering features such as anti-aliasing, and they control internally a memory limit, which we check to know how much data we can load before we need to reduce the quality even further to avoid crashes in the browser.
So just quickly, this may already be obvious, but just to make sure it is, we're always making a trade-off between the amount of data that we display and how well it actually performs and how much memory it uses. If it uses too much memory, it will crash. If you've seen it like snap in Chrome or crash in iOS in a tab, this happens when we use too much memory, essentially. We don't get any warning for that, it just happens. So we have to make sure we always stay kind of below that. And so we make this trade-off between showing a lot of data very nicely, but then becoming small and slow or potentially unstable. And yeah, we try to do our best, but in certain cases we can't make the right call for you, and you may have to influence it, and that's what Stefan will talk about.
Right. Here's just an example of the different, like the two extremes on the view quality. We have these two scenes. One is in a low quality setting where we also disabled shadows. So you see there are no shadows on that one. We disabled ambient occlusion. That's a bit harder to see, but you see that some of the areas which are denser, you have a more shadowy look on it. And it also uses the low quality profile. So you see that the low quality profile selects lower resolution textures. It's especially apparent on that building here. And it also affects how the atmosphere is rendered. So if I start an animation where the sun moves, you see that the sky rendering is vastly different between the two. But this one is also more expensive to render. And it displays fine here in Chrome, but on a mobile device that might make a huge difference. Now, a few hints on memory and quality, because we have seen that this is quite a common question for application developers and scene builders. In general, it's a good advice to reduce the numbers of layers you're using. In particular, map tile layers, I will have an example here, because each map tile layer kind of linearly increases the amount of memory we use to render it. And if you have things like 3D object scene layers, which might even be co-located, it's good advice to combine that data before publishing into a single layer, which allows us to be more efficient when loading that data and actually loading and rendering less data than having it in multiple layers. Obviously, or maybe not so obvious, but if you have scene layers with textures, textures tend to use quite a bit of memory. So maybe, depending on your use case, just having a nice non-textured 3D object scene layer might be an option, especially if you have just contextual data. And then other things which use a significant amount of memory are edges. Edges not so much, but they also use a bit of memory, and graphics. And one thing we will do, what Joe said before, for the different quality settings, we have different memory limits. We will internally monitor what all the layers are using in terms of memory. And if you add a lot of layers and we start to hit that limit, we will globally reduce the quality of all these layers to try to stay within that memory layer limit. And in really extreme cases, we will even start not to display some data which is further away in the background. I have an example for that. So this scene is, for example, running on a tablet where we have 400 megabytes available. Right now we are at a full quality because we are not yet under memory pressure, but as everything loads, you see that this percentage goes up and we just hit 100%. And then we will reduce the quality and stay still within that memory budget. And now everything is loaded. And I've here just extracted the data of how much of this memory is actually used by each of the layers. And we see that terrain is a significant amount of memory with 34%. Then the graphics for all the trees are almost 20%. The 3D object scene layer, since it's non-textured, is not so much, but the edges for that are also 9% of the memory. So what we can do now is, I know that, or I've seen that this one is using the most memory. So I'm using a simpler base map, which only has one map tile layer, and immediately that drops memory. Since it reloads, it goes up a little bit again, but you see now it's only using 15% instead of 34%. And we are back at full quality. So theoretically, you could stop here, but I will show you a few other things. Like, we have a lot of trees here, but we actually don't need to see that many trees. I just want to get a feeling of how many there are. So I set a limit on the layer view of that feature layer to 10,000. You see that there are a few trees which disappeared, but also the percentage of memory use dropped to now 17%. And the edges look really nice, so I would actually leave them in, but let's say you tried everything and that's the only thing which is left. I disable the edges, and then, of course, this one will drop to 0%, and now we are only using 200 megabytes of memory, and you could add more data to it.
Yeah, just one quick note on the maximum number of features on the feature layer. So, as you may know, in the last release, we've gotten rid of any kind of feature limit in the API. So you can point the feature layer with 10 million features at the API and it'll load some of them. What we do in 3D is we have a maximum number of features that we will display at any given point in time. And that's actually set to 50,000 right now. This may change in the future and may depend on the quality profile. Actually, it already does depend on the quality profile. So, but wherever you go, we try to kind of use those 50,000 features wisely to spread them in the view and make sure that you have as many features in the view as possible. But obviously that's one of the aspects that uses memory. So if you want to overwrite that, you can do that on the layer view of the feature layer. You can also try and boost it up and do 100,000, 500,000. You can see how far you can go. Maybe for your app you can put more, but at some point it'll just become slow and crash.
Yeah, and word of caution, if you actually set that feature, we will ignore the memory monitoring we do on that particular layer view. So you can really make the API use more memory than is configured in the memory limit. And then you crash, as Joe said, at some point. Then there are a few tricks also during data preparation which affect performance. So the most basic one is that you should publish your data in the same special reference as your scene, which avoids reprojection then for us when we get the data, and that obviously increases performance. And once you have published the layer, here are a few things which will also affect the rendering performance. Yeah, I'm not gonna read them here. So the first two ones are giving us a better rendering performance, and the last one will improve the loading performance, especially once you reload data, because it can come out of caches. Just a quick peek. For the external renderer, that's an advanced concept if you need to render data which we don't support, or you have a very special way you want to render that data, and you cannot visualize it with the existing layers and renderer and symbology. And then this external renderer allows you to write your own WebGL code to render within a scene. Of course, if you want to do that, you should be relatively proficient in writing WebGL and also be aware of the cost that has to write this renderer. There is a demo theater tomorrow on an external renderer where I will show a volume rendering, direct 3D volume rendering integration of a hurricane data set, which is not something we support yet, into scene view. So this is, let me play that again, just a time series of the water within that hurricane, how that moves over time. I will explain during the demo theater in detail how this external renderer works and show a few more nice visuals on it. And I think with that we are towards the end. Yes?
Yes, so a couple of pointers to sessions. The first one is the one that Stefan just described, so he's going to do that tomorrow afternoon. Check it out if you want to go crazy on WebGL rendering. Another interesting one here is if you have 2D data and you want to create 3D scenes, that's absolutely possible. There are various ways in which you can put your 2D data to good use in three-dimensional space. Raluca will talk about that in the second session tomorrow morning. And then finally, Stefan touched on various ways of visualizing things with points, with improved perspective and decluttering. All of these concepts will be explained in detail in the 3D visualization with the JavaScript API session tomorrow afternoon. Cool. I would like to encourage you to take the survey for this session. We really value your feedback, and we try to improve our presentations and make the best of it for the years to come. So maybe this is not so interesting for you, but your successor will thank you if you can give us good feedback of what worked, what didn't work, what we should improve for last year. And with that, we come to the end of the session, and we of course have time for your questions. Yes. Okay, so the question was how the views have a viewpoint property, and how does that relate to the camera? How is that incorporated? Yes, it does heavily relate to it. So if we look at the reference here, let's see, viewpoint for the scene view and viewpoint for the map view. It's not set here. This is a little bit obscure. If you look at the documentation for viewpoint, you will see that it has a couple of properties. It has a camera property, but that one is 3D only. So when you get the viewpoint from a 3D view, you get the viewpoint. But then it also has this target geometry, which I think in practice is typically a point. And in 2D, you get only the target geometry, whereas in 3D, you get the target geometry and the camera. So yeah, it's a little bit tricky to work with, but we tried to have as much compatibility as possible. It's just that in 3D, you have more degrees of freedom, so we need to describe more. Yeah, so does that answer your question? Cool. Any other questions? Well, that's not the case. We'll still be here. If you'd like to talk to us, come up to the podium. And other than that, thank you for sticking around and have fun doing 3D with the JavaScript API. Thank you.
Thank you.